The following is a recording of our in-person invited speaker series with Max Jaderberg. Max is a research scientist at DeepMind, where he leads the open-ended learning research team, known in the past for awesome work on XLand and StarCraft. He co-founded Vision Factory, which was acquired by Google in 2014, and completed his PhD at the Visual Geometry Group at the University of Oxford, under the supervision of Professor Andrew Zisserman and Professor Andrea Vedaldi. The title of the following talk is Open-Ended Learning Leads to Generally Capable Agents. But first, I'd like to briefly thank our sponsor, Fly Ventures. Fly Ventures is a pan-European pre-seed and seed stage venture fund. They have on-the-ground operations in Berlin, London, Paris, and Zurich, which gives them the opportunity to invest in the very best teams, regardless of location. Fly invests in B2B automation and applied deep tech startups, and specializes in day zero investing with significant technical risk. Some of their portfolio companies include Wave, GitGuardian, and Bloomsbury AI. And now I'm happy to present Max, talking about open-ended learning leads to generally capable agents.
Parts together. So obviously this is coming from DeepMind, and we have this idea of wanting to really build AGI. And I think like the thing that's becoming apparent is, there's going to be many different paths to this fabled AGI thing at the end, right? And this line of work, we believe, is sort of like just one of these possible paths. And maybe this paper, and I think this path is really thinking about focusing on the automatic generation of an ever-growing set of challenges for these agents. And we can do that by allowing full control over the environment side of things during training, without the need for human data, right? So there's maybe many other paths which are thinking more about how can we collect as much human data as possible, so at some point we get an AGI out of a big transform or something like that. This is maybe going on the other angle, saying, look, if we don't rely on human data, or just minimal amounts of human data, what can we do? And maybe the thing that we give ourselves is, okay, we have access to this environment, we can manipulate the environment. And so maybe this paper represents just like the tiniest step along this path, and something a bit like GPT-1 for RL. As I said, this, we published this in June. This was a real, collaborative team effort. You can see some of the amazing people here. And yeah, a lot of people had input on this. So I'm just sort of presenting on behalf of them here. So maybe the first thing is I'm going to show some results. So this shows some results of the trained agent on our environment space. These are like hand-authored tasks. These are probe tasks that we hand-authored to test the generalization capability of the agent. This is a single environment space which can represent things like capture the flag, games like hide and seek, where the agent successfully manages to like run away and hide. Games like King of the Hill, agent controls the top here. Even like physics tasks like stopping a ball rolling down, tasks requiring the agent to sort of build a ramp up here. And we find these agents are able to do this, even though this is actually really out of distribution from their training environment. There's 3-player games in this space. Here's a 3-player version of hide and seek with this like crazy hill that Nat McAleese actually made. Here's another capture the flag. I particularly like the capture the flag example because some of my previous work has been on human level performance on Quake 3 capture the flag. We were amazed to get to this point of like actually sort of getting to roughly human level by training purely on capture the flag. And then we set ourselves this sort of ambition of, can we get capture the flag without doing any training on capture the flag at all? And I think sort of 4 years ago, we would have thought this is absolutely insane. And now this is possible, just like not a good agent on capture the flag, but an agent which can do something, which I think is really cool to see. So hopefully this gives you a flavor of the environment and some of the results. But now sort of stepping back to like, how did we get here? We sort of started this project with this idea of like thinking about the environment itself. So if we think about our environment, and where life and intelligence has emerged, what we recognize is actually there's a huge diversity of environments existing in parallel, right? And somehow this life needs to exist across all of this diversity. And that's before, we even consider different worlds that could be out there, right? And so we're really, really accustomed to this idea of like, the perfect conditions for life. But in RL, we sort of just get given an environment and say, oh, this is the God-given environment, make it work, right? But I think that like the key question we wanted to start asking ourselves is, if we don't think in that way and actually like have control over our environment, the question is, what are the perfect conditions for learning? And when we think about this, then we think about these learning algorithms where we're constantly optimizing our environments to always provide the perfect conditions for learning for the agent at every different point in training. So this was our sort of starting hypothesis. Can we really like dig into this idea? And we needed an environment for this. We thought there wasn't anything sort of quite readily available for this. Why? Because we want something that's fast and parallelizable, that has some underlying consistency, right, in the space, so consistent physics and rules, but that can support a very vast number of unique tasks, really large diversity in terms of like the physical properties and states that could be encountered, but also large diversity in terms of the goals that are being asked of the agent, and a crucial property, which is smoothness, the ability to smoothly change this environment in some sense. And we'll dig into what these properties of vastness, diversity, smoothness actually mean in practice. And then the sort of cartoon idea is like, oh, can we get like an ImageNet for RL where there's so much diversity on the task side, not on the observation side. We don't care about observations. We care about tasks that are being asked of our agents, right? There's so much diversity on the task side that just with enough tasks and big neural networks will get generalization over task space. It's nothing complex. And so to try and like address this environment problem, we came up with this environment we called XLand, which is a multi-agent environment which consists of procedurally generated worlds and procedurally generated games. And we can think of an environment instance, a particular episode, an agent gets a task. That task is composed of the physical world, what's the map that's being played, with the game that's being played, what's being asked, what are the goals of the different agents in this multiplayer game. And then also the policies of these agents, because the same game with agents which behave very differently can be asking very different things of an agent under test. So there's sort of these three main dimensions, independent dimensions. Here's a visualization of this environment space. On the left, you can see this, what we call the galaxy of games. Every dot here, these are evaluation games in our evaluation space. Every dot here is a particular game where you can see there's some games like Capture the Cube, something like Hide and Seek or Match the Sphere in a Cube. This is actually like, I think it's a UMAP representation of these games. This is really data driven with the color representing the competitiveness and the size, the balancedness. Each one of these points is a game, and a game can be played on any number of worlds, right? So these things are independent. So if you zoom into like this particular point, you can see like an example of all the different possible sorts of worlds that could be played, this game could be played on. And here you can see some examples here. There's sort of a variety of topologies and layouts. And at the bottom is this sort of equation of a task. A task is this combination of a game, a world, and then the co-player policies. So a lot of this work, like we're sort of ignoring the multi-agent RL aspect for simplicity, and just thinking about a single agent playing in a world which is inhabited by other agents. So we think of like a player, and then its co-players, right, which are like almost part of the environment space. Here's a bit of a zoom in on what one of these tasks look like, just so you can see there's, you have the topology, things like the white floor or the orange ramp or the blue floor. You have these objects like spheres and cubes and pyramids. You've got, in this example, you've got 2 players. It can be up to 3 players. You've got a red player and a blue player. The game is the set of goals. So things like here, the blue player has the goal, see red player or stand on orange floor. And the red player has a goal, put purple sphere near black pyramid. And then from a single agent's perspective, so from the learning agent's perspective, you have this thing on the right, which is the observation that the agent will get. This is just the first person RGB view, and the goal of just that agent itself. So hopefully this gives you a flavor of what the environment sort of looks and feels like and what the observation space is for the agent. So I'm going to talk a little bit about how we create this environment, because I think, the whole point is like the environment is as important as the learning algorithm in this space. So first, on world creation, there are these three parts: world, game, co-players. World creation, we procedurally generate these worlds. It's using this nice little method called wave function collapse, but it's essentially like a constraint propagation mechanism where you have these set of tiles. In our case, it's pretty boring. It's just like the different floor tiles and ramps that connect, but there's constraints saying that a ramp can only connect, the two corresponding floors. Then you start sampling the space and propagating the constraints, and you build up these height maps, which you can then, translate into real Unity game objects. Then you have things for the object spawn. So where do these spheres and pyramids spawn, and where do the players spawn? These we represent by, for example, a CPPN, which acts on the map. So it's like these compositional pattern producing networks. Just a nice way to sort of represent a probability distribution, which is conditional, highly conditional on X, Y, height, tile location, all this sort of stuff. And the cool stuff about it is it can be evolved quite easily. And we just sampled from that. One of the key things though about this wave function collapse algorithm is you can actually quite easily convert it into a mutation operator. So you can take a given world topology and then conditional on that mutate to a new world. This is what you can see in this GIF. It's just like step-by-step mutation of this space. You can see some examples on our real worlds on the right here. I think that was an early prototype. And this maybe gives us a mechanism to have some sort of smoothness, even though it's a discrete world space. Clearly, there's some sort of notion of small changes in world space. And okay, what can we do if we have this procedurally generated world space and we have this smooth mutation operator? Well, we can do world agent co-evolution. So, and we actually do this in sort of like a standalone offline job to create a very rich set of worlds that could be trained on. So how this works is we have an agent. It's just a single agent game where the agent is trying to find the yellow pyramid, right? And then it's a co-evolution process between a collection of worlds and the agent, which is training with RL, trying to maximize return on finding the yellow pyramid. And the fitness of this and this collection of worlds can mutate under a genetic algorithm, where the fitness is something like the variance of return of the agent. So it's trying to find worlds that the agent 1 in 10 times can solve, right? So it's a solvable world, but a not very solvable world. And that builds up a training distribution, which then the agent is fitting RL onto, and these things sort of ratchet up. We run this training process and we checkpoint all the intermediate worlds that come out of this place. And this gives us a natural curriculum of world topologies from very easy, like the starting point of just a blank canvas, to very complex worlds that come out of this, which have, some really nice structural properties that we didn't humanly encode, things like really long paths or navigation with cliff edges that the agent can fall off and have to start again, or worlds which actually have many different forks. So the agent, has to explore all this stuff. So we use this process to get a really rich world set. And out of this, we have sort of, kind of satisfied these ideas, at least on our world side, for diversity, vastness, and smoothness. We clearly have a diverse set of worlds. There's lots of things that can be represented here. On the vastness, we can do some sort of simple counting stuff to show that actually there's a huge amount of stuff in this space. And the really interesting thing is on the smoothness, we can, these graphs on the bottom are trying to, there's like a theoretical line, which is this pink line, and then there's the empirical points. actually, no, sorry, there's no theoretical results on the world side. But these are just empirical points. On the x-axis, you have the edit distance of a world. So this is like, if you flipped one tile, that's sort of one distance in the x space. And on the y-axis are two different measures of emergent properties of the world. So one is path resistance. So how easy is it for any two pairs of points in the world navigate? What's the distance to navigate between them? So that's sort of one emergent property of the world we might be interested in. And then another one is this another form of resistance, which is like the like what is the bottleneck state for these worlds. So these are two different ways we can, like, some properties of the world that we might be interested in, and we can show that as we wiggle the tiles of the world a little bit, we get small changes in these emergent properties, which kind of satisfies our smoothness property, that we can do a little bit of mutation and the emergent properties will change a little bit. At the same time, we can also do, as we do many steps of mutation, these properties will change a lot. So these are really good characteristics to have. Okay, so now I'll talk about the game side. So the way we represent games are in this sort of logical language form. So it's a structured language, fixed grammar. Here's an example game where player 0 has the goal C player 0 player 1, and player 1 has the goal not C player 0 player 1. And I don't know if you can guess what this game is, but it's a game of hide and seek. So, you know, we represent games like hide and seek in this logical format where it's just a graph where you can fill in these nodes, where you can have relations, things like see, touch, far, near, acting on objects like the avatars, these red and blue players, the cubes, the spheres, the pyramids, all this sort of stuff. So this is the example of hide and seek. These sort of base level relations and objects, we call the combination of these, we call predicates. It's sort of a mapping of state into a binary, you know, into a binary 0, 1. There's around 200 atomic predicates in XLand. You can see things like C, black cube, me, right? Or near, yellow cube, yellow sphere, right? You want to make these things near. And so you can combine these base level predicates in with like an or and with and. So you can have like an option, which is composed of anding multiple of these things, and then oring between these options. And this is like a canonical binary logical form of sum products form. And this gives us a game space, which is really large. Just like on the world side, where, yes, you could kind of randomly sample these worlds, but actually it makes sense to do this like agent environment coevolution to get interesting worlds. We have the same problem with games, where if we just randomly sample, you know, these logical statements, we might not really get a distribution that is the most interesting we could get out. And I think the key thing is we started to look at some properties, emergent properties of worlds, of games, the two in particular, competitiveness and balancedness. How competitive is a game and how balanced is a game? And we can see that if we uniformly sample the game space, you get this sort of distribution in competitive and balanced space represented by the blue graph here. And this is nice, but it doesn't necessarily capture the extremes very well. And so we have a rejection sampling process and a mutation process, which can like adjust this distribution. So we oversample and skew the distribution to cover much more uniformly, hopefully, in this competitive balancedness space, right? Again, it's this idea of, you know, there's a base distribution of the world or base distribution of the game if you uniformly sample from this. This might not be what you care about. And so there's maybe a process by which you get a resulting distribution, which is much more aligned with the emergent properties with respect to agents that you do care about training on. Yeah, question. Balance is like a perfectly balanced game is one where both sides have to do the same thing. So it's the number of common predicates, underlying predicates that the agents have to satisfy on the two sides of the game. This analysis is done with two agents only. Competitiveness is how many of the predicates that the agents have to satisfy on either side are in conflict with each other. So a purely competitive game is where one agent wants to see the other player while the other player doesn't want to be seen by that agent. So it's a pure not, right? Purely competitive where they have exactly the same on both sides. But then there's so many games in the middle, some are completely independent. There's like, you know, I want to get that cube and you want to get that cube. That's completely independent. But then there's some like mix of competitiveness and independent and cooperative, where like, I want to get that cube or I want to get that cube, right? So that's kind of 50% cooperative and 50, whereas, you know, rather than fully cooperative, or I want to get that cube or prevent you from getting that cube. That's 50% competitive. Yeah.
Fully cooperative? You're fully cooperative?
Fully cooperative as well. Yeah. We both want this cube to be next to that sphere.
And for the ones where it's fully independent, is there still a competitive, I guess, aspect to it that whoever gets there first basically wins? Or
No. The only competitive aspect that might arise from a fully independent thing is that one policy might just want to tag another agent and get rid of it, right? Or just like mess things up just for the sake of it. It's not like, so this sort of analysis, these properties are done with these like ideal meta agent, you know, ideal agents in mind, not with like real policies.
We're both agents using the same policy.
We're both agents using the same policy. Again, it's this like simplified model where the agents, these aren't real agents that we're measuring here. These are like agents which are assumed will achieve that, will try will sample the predicates out of its goal and achieve that automatically. So it's kind of like a simplified agent model that we use for this metagame analysis. It's quite a common thing that you can do in like combining game theory of multi-agent RL. So I have these simplified ideal agent models. Yeah.
When you do the generation of the games, in terms of like the game represented by the goals and topology, is there any conditioning where, say, like certain games might have no solution for a given topology? Like if the game is like you have to get the blue cube of in topology, or is it just you're actually just doing like domain randomization on both of those sets?
Yeah, it's a good question. We enforce the world space so that it always has all of the objects. So we know that everything is always satisfiable. And we also only create worlds that have no we call them death pits, you know, where like you could fall in and never get out. So again, it's just to remove this confounder of like, are there impossible worlds? Are there impossible tasks? Like obviously we've got bugs in our generation code, so we do get them. I'll talk about like the evaluation metric, which gets around that. But ideally, yes, that like everything's satisfiable, and we know that, at least under our simplified agent movement model and all this sort of stuff. Yeah.
An association between the topology of a given environment and the sort of like competitiveness or independence of different agents within a given game.
Yeah. So these things are like real competitiveness and real, you know, balancedness of a task depends on the combination of the goal with, you know, the game with the world, the instantiation of the world. We don't analyze that. It's actually a really difficult object to analyze. So like when we're doing this analysis, we're just thinking about a game independent of what, you know, sort of think about it like marginalizing out the world that it's played on. And when we think about a world, we think about a world marginalizing out the game that it's played on. I think like open question is how can we, like, what are properties of tasks and how can we get those out quite easily? It's really difficult actually. We're like, yeah, open question, yeah. Yeah. Yeah, absolutely. So when we did this agent world coevolution, this was only on the game of find the yellow pyramid. So one of the simplest games you could possibly have. And so you get very complex topologies, which make it hard for that simple game. Now, even with like just, a flat open room like this, you can have very complex games, or like at least very like games which have no sort of stationary solution. Like you can think about it like iterative rock, paper, scissors style games, where, yeah, even with a very simple world, you can have very complex emergent dynamics. Yeah, I'm going to move on a bit just for time's sake. Again, we can measure these things of vastness, diversity, and smoothness. I think vastness is easy, like just it's combinatorial space. There's a huge amount of games here. Diversity, here's some examples. You can have capture the cube in this space. You can have cooperation games, hide and seek, lots and lots of different like things that you can get out of this. And again, in smoothness, actually now there's some theoretical bounds which are backed up by empirical points of, again, on the x-axis, you have this edit distance. If you flip a predicate or an object in this thing, how much does it change an emergent y-axis property? And the y-axis things are things like competitiveness on the right graph. And I think kappa is like exploration difficulty. So how hard is it to find these things? Oops. So yeah, smooth games, again, it's still a discrete space, but little mutations will change things a small amount. Okay, so we have an environment space. At a high level, it seems to meet our like, criteria. And now we want to create these generally capable agents. The question is, what do we even mean by generally capable agents? We want this like fabled AGI thing. What do we actually want out? These are the sort of things that we were thinking about, like these three statements. So first of all, we want agents which should catastrophically fail on as few tasks as possible. We don't want to like stick our agent, like, or someone comes along and designs a new task, and you put your agent down and it just does nothing. Like, that's embarrassing. We don't want that. On the other side, we want our agents to be as competent as possible on as many tasks as possible, right? So if you do put your agent down on a really simple task, it should probably be able to do it pretty well, right? And we'd love that across as much stuff as possible. Let's say like, human level or superhuman level on as many tasks as possible. And then the third criteria is that we care about broad ability over narrow competency. So you could think, oh, you might get this like competency, but on a very small set of tasks. Actually, we don't care about that. We want broad competency. And I think the thing to recognize is these things are in conflict with each other. Like, you can't necessarily just push up one scalar which maximizes all of these three things, even though these are words. Like, we couldn't find a way to like put this into a single scalar. And I don't think it is possible. So instead, we have to think about what are some multi-dimensional sort of evaluation metrics that we can push up in a Pareto sense to that sort of like encapsulate these three things. And this led us to this idea of normalized percentiles, which I was saying to some people earlier, is like one of the breakthroughs that we had was just finding an evaluation metric that we could just forget about everything else, throw the kitchen sink at this thing and try and push the numbers up. And so this is a really simple idea. We have a big evaluation set of tasks, think thousands, right? And for each one of these tasks, our agent is given a score on the left, right? And you can then think of the agent score, and then like we look at our catalog of agents that we already have, lying about because we've trained some things before, and we can find for each task we can find the best agent score on that task, which is this sort of light blue bar, and then we can just simply normalize by this. In an ideal world, we'd be able to get humans to play these tasks, but if we've got thousands, and we could normalize by human score like you do in Atari, but we've got thousands of tasks, we can't possibly do that, and we want to create more and more all the time, right? So instead, we normalize by the best known agent score, and then we simply sort these normalized scores from lowest to highest, and you can think of like fitting this sort of forms of distribution of normalized scores, and then given this sort of distribution, it's a bit like a histogram. You can look at the percentile. So percentile 50 is what's the median normalized agents normalized score. That's kind of interesting. I'll just finish and then take some questions. but then you can, you know, that's maybe interesting, but encapsulates lots of very, very competent behavior. And what becomes really interesting is when you look at the tail end of the percentile, so percentile, you know, 10, percentile 5, or, you know, percentile 0 is the worst case. This might also be really uninteresting because, as I said, we have some bugs, right? I think we all do. There's always going to be a task which is impossible for our agent. So percentile 0 might always be 0. But maybe what's interesting is what's the smallest non-zero percentile that we encounter. So this gives us a set of numbers from percentile 0 to percentile 50, for example, that encapsulate the sort of variety of behavior across performance criteria. And the idea is if we can push this up in a Pareto sense, and we only say one agent is better than another if it dominates the other agent on every single percentile, then we can use that as a metric to push up. If they overlap in any way, then we can't strictly say that one agent is better than another. Cool. Questions? Oh, good. Oh, yeah.
Yeah, just to make sure I understand. So you don't take the best performing agent. You take all scores and normalize across all scores of that task, right?
Take all. We take
to get the normalized.
We take the best performing agent on that task and normalize that particular task by that best performing agent.
So you don't take into account the distribution of the scores of all agents in this task?
No, we just take the best one. Now, this works in our setting because we've only got a small set of agents. So it's none of them are overfit to a particular task, so to speak. There's like there's a lot that can be said on this, but there's probably not enough time. But this is almost certainly not optimal. And there's a lot of like interesting theoretical properties about these sort of metrics. So I think there's a lot of exploration here to be done. The cool thing about this metric is we can update it iteratively, because this best known score is agents that we have lying about. And as we train a new agent, oh, well, that goes into the set of agents that we consider to normalize. And so the nice key property about this metric, when we use it in this iteratively updated manner, is it's actually open-ended, because there's no boundary of score that could be achieved. There's no saturation point. You know, when you consider an infinite number of tasks, or like seemingly infinite number of tasks, you can just keep trying to like push out, you know, behavior in this space. Yeah. Yeah, you fix the game and world, and then just like find the best, the best opponent, Okay, we've got an environment, we've got a metric. Let's try and push it up. We need a training algorithm. Yes, question. Yeah, this is like an argument that we've literally been having this week and last week internally, and it comes up again and again. Like intuitively, it feels like, can't we just like train an agent on this particular task? And that's clearly the best thing that could be done on that task, right? And that's true if you only consider that task in isolation. But we want an agent which is like general and can play many, many different tasks. So if you think about like, if you think about an example task, this is like a key point. Like if you think about an example task, which is a bit like a T-maze, where you have to do a lot of stuff. Like initially you have to choose, do you go left or do you go right? And then you've got a really long path to get the thing. So basically you have one choice, do you go left or right? And, you know, are you going to succeed or not, right? You could fine tune an agent which will always go left because that's where the particular thing is. And so that like, but that is an impossible policy to achieve when you consider all the possible environments that could be there, including the same exact one where the cube is on the other side, right? So the optimal policy with respect to the distribution of tasks is different from the one that is fine-tuned on that particular task. And yeah, I think actually, like, you know, Wojtek in my team has probably the most theoretical understanding of this, and like really advocates for this idea of yeah, not using the fine-tuned best one, but maybe more of a generic best one. Looks like pizza's arrived, which is exciting. All right, we're going to train some agents. We've got a training algorithm which is sort of composed of three layers of dynamics here. On the set of days, so like the slowest sort of updating thing, we think about training generations of agents, right? Where out of a generation, we get a population of agents, a set of agents, which are hopefully better than the previous generation. These generations provide better policies, and they also provide new players that you play against in the next generation. And they also provide new agents, which you can compute that normalization factor for that metric for the next generation. And each generation is bootstrapped off the previous generation by using policy distillation to distill the best agent from the previous generation to sort of like kickstart the next generation. So that's a process that happens at the sort of cadence of days in our training setup. Then on the timescale of hours, we have population-based training acting within a generation. So here in PBT, you're training a population of agents, and you can mutate the hyperparameters of these agents, things like learning rate. But crucially, in this scenario, we can also mutate the parameters of the task generators themselves. So when we're as the training is occurring, the agents train on a distribution of tasks, instantaneous distribution of tasks, which is given by this generating procedure, and we can use PBT to actually control and modulate that. So the distribution of tasks, the properties of tasks will change as the agent is training. And the fitness we use for PBT is again this normalized percentile metric, and it needs Pareto dominance for one agent to be considered better than another. Yep. It's population-based training. It's a simple genetic algorithm which looks at which agent is best, and the best one it'll destroy the worst one, mutate the best one, copy the best agent, and then mutate the hyperparameters, things like learning rate or distribution properties, task generating things. Cool. And then at the sort of fastest level of seconds, we actually do RL within an agent on trying to maximize expected return. We use off-the-shelf sort of VMPO for this. It's just trying to maximize expected return, but expectation over what? Well, it's over the instantaneous task distribution, which is itself being modified by PBT, and so is dynamic. So you can still use RL to maximize expected return, but the distribution over what you're doing expectation over is constantly changing. And so yeah, this process acts all together. There's some nice sort of neural network architecture that we use to condition goals on. I'm not going to go too much into this, but I think suffice to say, we exploit the sort of this logical structure of the goal space of having different options. So internally, the agent models the value of each option and does sort of selection, does attention on its LSTM based on this. But I'm not going to go too much into this. Cool. I will dig a bit into this population-based training. As I said, we're evolving the parameters of the training task generators. When I say task generator, this is actually a really simple process. It's actually more like rejection sampling, right? We sort of sample a new task from the base distribution of worlds and games that I was talking about before. And then we run the agent for 10 episodes and collect those returns. And we also run a random action agent for 10 episodes, right? And then just using this, we ask a few simple questions. Does the task require something more than a random action policy, right? So we want the random action agent to get 0 on this task. Otherwise, it's like a trivial task. Then we ask, is the task too easy for the agent, right? So if out of those 10 runs, the agent is always getting some return on every single one of these tasks, maybe it's too easy. Then we ask, is the agent able to do something better than a random action policy. So, you know, there's some leeway for this random action policy. It's allowed to get some score. And is the agent getting more than this score? Now, the thresholds for these functions, like how much is a random action agent allowed to get? How much more does the agent need to get than the random action? What threshold is considered too easy for an agent? These are hyperparameters and things that PBT controls, right? And so that's how the task distribution is changed. Okay, so we do some training, and this is actually an overview of the entire training process of the paper. We trained 5 generations in total. This took a long time, probably like 6 weeks or something to complete. Yeah, you can see here, like generation 1 starts, there's a few different metrics that we're tracking here, things like participation. So this is like the percentage of games that the agent gets some non-zero reward in. All these results I'm going to show now are on you know, test sets, so things that agent hasn't seen in training. We also have this idea, like a hand-authored set of tasks, like probe tasks, and we track return on that, as well as percentile 10 and percentile 50, the median and the 10th percentile score. And we can see that every generation, the agent is getting stronger on some part of this metric space, maybe not on everything, but on some part it's pushing this up. And so in general, it's sort of Pareto dominating the previous one. We do some ablations to see, you know, what parts of this training pipeline really work and what don't. I think like the crucial thing is really this like dynamic task generation, this process of like rejection sampling tasks. PBT also makes a nice difference for this, as does this goal attention architecture that I didn't talk about. And we can see evidence like of this process of generational training actually being better than just keep training the same agent. And this is a bit of a quirk with deep RL and neural networks, where actually, as you train a neural network, the plasticity of the weights almost like contracts and things get really stiff, and it's hard to learn new things as you get further and further in training. And it can sometimes be beneficial to stop training, restart training, distill from the previous agent, and you'll actually like start to exceed your teacher, even with it, like if you let the teacher run, and that's what we're seeing here. Other things like methods you see in deep learning literature like this are things like cyclical learning rates, where you sort of restart the learning rate and shock the network back into like some more plastic state. Deep learning dark arts. This shows the percentiles of the final generation of training. Maybe the TLDR is things get bigger, but I think the key point is like, if you look at below, we've got some examples of some of these hand-authored probe tasks. Now the top is this automatically generated evaluation set based on the world and game generating process that I was talking about before. We don't really know the specifics of what's in these thousands of tasks, but then we sat down as a team and sort of came up with some little tasks by hand, like, you know, capture the cube, hide and seek, tool use, ridge fencing, you know, blah, blah, blah. When we measure performance of the agent on that, we see that it actually sort of correlates to how it's doing in percentile terms on this automatically generated evaluation set, which is cool. This means we can automatically generate an evaluation space, and we kind of know it translates in some sense to expected return on like hand-authored probe tasks we might want to do at test time to probe our agents. I showed you this video of results, so I'm going to show some particular results here. These are all on the hand-authored task. This is this task stop roll, where you get a reward when the purple sphere is not touching the red floor, and also the player is not holding the sphere. So agent has to sort of get the sphere off the red floor without holding it. Why is this hard as a game? Well, it's only hard when you actually look at the combination of the game with the world, which is to your point, like, how can we measure these properties? I don't know. But yeah, obviously it's just going to roll down the whole time. So we're going to see what the agent does. This is sort of the best trained agent. It's picking up the sphere and for some reason seems to just take it up and let go of it and start kind of blocking it with his body. This is a very physical task, right? Like a physics-based task. It's unclear how much of this stuff is seen in training. This is sort of consistent behavior that we see over and over again, of sort of taking the sphere up and letting it roll down. Sometimes it seems to even discover, like within an episode, where is it? Yeah, here we go. This is quite cool. It's sort of playing around with it and then manages to wedge it against the boundary wall and just stays there. It kind of knows, okay, this is great. I'm just going to stay here and chill. Other times it just ends up, you know, through this like kind of semi-random playing with the ball, with it on top of this wall object, and it's just getting reward because it's off the floor. And again, it just stays and stops playing with it. Again, similar to this, we see these examples of two types of multiple behaviors from the same agent in the same situation. So here the agent has to get the other agent off the red floor. So it's kind of gone off the tower and gone round and gone up the floor, tagged the other agent to get it off the floor, and then it lifts it up a bit like Simba and just holds it off the floor. The same agent can have another behavior where it just goes to the edge of the tower and just repeatedly tags that agent. These are just like, it's a stochastic policy. Sometimes it flips into these two modes. It's really cool to see multimodal policies come out of RL. I think a lot of people said that isn't possible. We also see agents actually using tools. In this example, you have to get to the purple cube, but it's on top of this plinth and there's no ramp to access it. This is actually completely outside of training distribution where this would never happen in training. The agent sort of randomly throws things about and like ends up freezing this ramp. It's got a freeze gadget and using it as a ramp to get up to the pyramid. In another episode, what does it do? Again, it's just a bit frustrated, maybe randomly throwing things about. Somehow manages to create this ramp and uses its own body weight to like get up on there. Again, another episode, still frustrated, things are flying about. The agent just kind of just plays with things and happens to throw and hit that object out. Is this directed? You know, probably not, but it seems to work. So like something about this sort of random undirected behavior consistently leads to satisfying the reward. It's kind of strange. It's counterintuitive. And that kind of leads on to this like golden behavior that we found, which is this idea of experimentation, where here the agent has to get these three cubes next to each other, but without one of them being far away from the other. So there's a specific spatial arrangement of these cubes that will get the agent the reward. But the agent clearly doesn't know how to achieve that. So it's just sort of randomly placing these cubes next to each other. It's never happy, so it keeps changing things about. Sometimes it just randomly happens to get into the rewarding state. At that point, it can recognize that and just stop touching those cubes most of the time. Again, this is a consistent behavior we observe in this level. Like the agent doesn't know how to solve it, is randomly playing with things, eventually hits the rewarding state just from entropy, but does recognize the rewarding state and leaves things alone. It's a really cool meta heuristic behavior to allow an agent to solve a generic set of problems that it might not know how to solve up front. This is kind of the key part of generalization that I think we're going to see from RL, which is quite distinct from the sort of generalization we think about in supervised learning. I'm going to skip over some of these examples. We do a bunch of internal representation analysis to understand what the agent knows about, and it clearly has an idea of, is it in the rewarding state? How much do I, like, how far away from the rewarding state am I? I said we don't touch this multi-agent RL problem. We always train in this best response setting, and we just add in a new agent from the previous generation. So there's a tiny bit of multi-agentness in that. But we can, like at test time, so after the agent is trained, we can take checkpoints of the agent and see how it evolves in terms of its collaboration. We had this amazing intern, Anuj, from Shimon's lab, who did these experiments of encoding things like social dilemmas into XLand game space, and then observing, do the agents cooperate or defect, and seeing how that emerges through time. And high level, they seem to get a bit more cooperative, but there's probably a lot more that can be done on this. And then the final result that I'm really excited about is this idea of fine tuning. So, like, why do we want this agent in the first place that can do lots and lots of different things? Well, maybe we can think of this as like a pre-training mechanism, right? Where we don't know, what our end goal for this agent is going to be, but we want it to do lots and lots of stuff on this environment domain. And so then at test time, we can come along and say, here's a new task. And yes, there's some zero-shot performance, and that's maybe our orange bars. But then we can think, okay, what if we just did a bit of fine tuning? And so this is literally, half an hour on our Google, compute of fine tuning, but it's 100 million steps. So like, this is maybe a Atari training scale. We can get these agents fine tuned really well on these complex tasks where, zero shot, these are the blue bars. From scratch on the blue bars, you would often get no behavior coming out because they're really hard to, just from the exploration point of view. And this I'm really excited about, like thinking about this idea of open-ended learning on vast spaces to get these, generic latent conditioned agents, which can then down the line be fine-tuned to complex downstream tasks that they've never been trained on. That seems like a really rich space to explore. Cool. That's pretty much it on results. Where we're going with this, we want to really be thinking about, beyond this sort of zero-shot behavior, thinking about few-shot behavior, and really observing adaptation of the agent behavior within the episode over the course of minutes. I think it's clear we're sort of starting to achieve, generalization, like zero-shot generalization, but the agents aren't adapting. You saw in that experimentation example, it does it once, but then once it gets the right state, it can't remember that state and quickly get back to it. So, that's why I say it's a bit like the GPT-1 in RL, because there's some sort of like nonsense being produced and it's kind of coherent and it makes you smile, but it's not actually, adapting to what you're prompting it with. So that's kind of where we want to go. There's lots and lots of like rich research in the space, but I'll quickly open for questions before we run out of time, I think. Yeah. Question?